Okay. All right, so you got to understand where this concept comes from and how it relates to what you learned last time. So if you remember last time, there was a rotation happening every time, right? And therefore, due to that rotation, any cross-section or slice of the solid will always be a circle, right? Got it? I mean, if you think about it, doesn't really matter what the starting shape was. Really doesn't matter. When you rotate it, right? When you rotate it around, it's going to look like that. And if you slice it, is it going to be circular? If you take a slice right through the side, won't it be circular, the slice? Same thing here. If you rotate this, again, no matter what it looks like, again, if you slice it like that, won't it be a circle no matter what? And that's due to the rotation, right? Got it? Okay, so if you look at that and then look at the formula, which was that, and by the way, is it okay if I put the pi back in like that? Right? It's a constant. It doesn't really matter if it's inside or outside the integral. So if you put it back in, and then you look at this part of the formula, don't look at the dx for right now. Just look at that. What is that? That's the formula for what? Area of a circle. And then if you want to know what the dx is, like I explained last time, that's your width. That's what turns a circular slice into a thin disk by putting the width or the delta x in it. Does that make sense? But the bottom line is, what's right there in front of the dx? The area of a slice, which is a circle. Is that clear? Okay, so with that in mind then, that's what we're going to do today. We're going to talk about situations where you don't end up with a circular slice. And by the way, those slices actually have a better name. They're called cross-sections. Got it? So when I talk about a cross-section, think of it as a slice. Okay? All right. So it's real simple then. Today, I'm going to describe a situation, and I'm going to tell you what the shape of the cross-section or slice is. And so guess what goes right there in the formula then to find the volume of such solids? Guess what goes right there? The area of the what? The slice or cross-section. Okay, and just know that, again, everything's in terms of x dx from an x to an x if the cross-sections are perpendicular to the x-axis. If the cross-sections or slices are perpendicular to the y-axis instead, well, then everything would be in terms of y dy from a y to a y. So again, just know the difference there. Okay, important note. Okay, so the formulas I just showed you will now allow us to find the volume of a solid that is formed without a rotation. So there's going to be no rotating today. Okay, but instead, I'm going to start you out with a two-dimensional enclosed region as the base or bottom of the solid. And then I'm going to extend into a third dimension using a given cross-sectional shape. So I'm going to tell you what the shape of the slices or cross-sections are. That's going to be part of the given information in each problem. Okay, so here are some examples. All right. Suppose you start with this right here. Okay. That two-dimensional region. And what's going to happen is pretend like that's the bottom of a solid, and then you're going to come straight up off your paper into a third dimension. Okay, so again, that's the bottom of some solid. Okay, like the bottom of the stapler, for example. Okay, that's the bottom. And then you're going to come straight up off your paper into a third dimension using cross sections in different shapes. So, for example, what if I tell you you're starting with that triangular base or bottom, then you're coming straight off the page into a third dimension using cross sections or slices that are semicircles. Okay, so even though it looks like I drew those semicircles sideways, they're actually coming straight up off the paper into a third dimension. Does that make sense? Same thing here. This time you're coming straight up off your paper in what shape? Cross sections or slices. What are they? Triangles. Well, suppose they're equilateral triangles. Okay? The formula for an equilateral triangle is square root of 3 over 4 times your base, which is this, squared, Backing up over here, what's the area of one of those slices, guys? Well, 1/2 pi r squared, isn't it? Because they're half circles. And then again, suppose, again, you're starting with the same bottom, but this time you're coming off the page into a third dimension using what? What type slices? Squares. And what's the area of a square? Side length squared. Okay? Again, let me see if I can find you a better example of what this might look like. Okay. So again, suppose you're starting with a two-dimensional circle, okay, on an XY plane, and then you're coming straight up off the paper using squares, okay, that are perpendicular, say, to the x-axis. You see how you have a bunch of squares that are stacked next to each other, perpendicular to the x-axis, and so that's what the three-dimensional solid will look like. So what's happening is this. If you start out with a circle on an XY plane, okay. Here, let's do a better one. Ready? Suppose you use equilateral triangles. That's what it'll look like. Okay. Suppose you use semicircles. That's what it'll look like, kind of like an igloo. Suppose you use rectangles. That's what it'll look like. Okay. And suppose you start with a triangle on the XY plane. Well, it's kind of hard to see. How about if you start with a square, and then you use semicircles? You see how the different solids you're getting, guys? Okay, so what's happening is you're stacking a bunch of those semicircles next to each other, side by side, going straight across the region. All right, I think the best one is starting with a, let's see. Yeah, those are kind of hard to see. I don't like those. But this one's pretty good to see. You can see that one. That one's pretty easy to see. Let me describe this one. So if you're starting with a circular base on the XY plane, and then you're coming straight up off the page into a third dimension using triangles, suppose they're equilateral triangles, is it going to kind of go like this, guys? I mean, basically, I shouldn't have drawn it that way. Basically, here. So hard to draw. Basically, that's the bottom of your triangle, and then you're coming straight up off the page using the two sides that are just as long as the base. So if you're over here, obviously it's not going to go as high, right? If you're over here, it's going to go really high, isn't it? If it's equilateral. You see what I'm saying, guys? Again, those are coming straight up off the page into a third dimension to form the solid. So you just have an infinite number of those triangles stacked next to each other, starting here and ending here. Good? You understand what we're doing? Okay, and then it's real easy. Okay, once you get the idea of what you're doing, this is actually pretty easy. Okay, so all right, so here's example 1. Okay, so the first information I give you right here forms the two-dimensional base, in other words, the bottom of the solid. So let's graph those. Okay. So you've got the line y equals negative 2x plus 4. I'm just going to plot some points. 0, 4, 1, 2, and 2, 0. Okay. So you have this line here. You should be writing this down, guys. And then you got the line y equals 0, which is here. And you got the line x equals 0, which is here. So the enclosed region between those three things is right here, isn't it? Okay, so you can erase everything else now. Okay, so we're starting with that. Okay, now what else does it say? It says the cross sections or slices are semicircles perpendicular to the x-axis. Okay, so here's what's going to happen. Okay, so what I did is I drew a line segment perpendicular to the x-axis from the top to the bottom. And then what's going to happen is I'm going to come off my paper like that using a semicircle. Okay, if I do it here, it'll be really low. Over here, it's going to have a higher ceiling and so on. So the more left you go, the higher it's going to be, isn't it? Do you understand? And so what we're going to need then is we're going to need the area formula for a semicircle. What's the area formula for a semicircle, guys? What is it? 1/2 pi r squared. Okay, and so what we need now is the radius so I can stick it in there. Does that make sense? And so we need an expression for the radius of one of those semicircles. So if you look at it closely, guys, look at it closely, I think you will agree that the radius of one of those semicircles goes from here to here, doesn't it? Isn't that the radius r for one of the semicircles? Isn't it? Okay, and what is the distance from the x-axis halfway up to the curve? Isn't it just 1/2 the y values on the curve? Isn't it? And so the radius is 1/2 times the function. What's the function? What's the function? Yeah, negative 2x plus 4. Does everybody agree that negative 2x plus 4 gives you the distance between the x-axis all the way up to the curve, doesn't it? But I don't want that. I want the half of that because I got semicircles, so I'm looking for an expression for the radius of one of those semicircles. So just take half of those y values in terms of x. Does that make sense? And by the way, what does that simplify to if I distribute the half? Negative x plus 2. All right, so that's going to go right here in place of the radius. Okay? Now, whoa, that was strange. Okay, so at this point I'm going to simplify that mess, so here it goes. Here I'm going to FOIL x squared minus 4x plus 4. Okay. Yeah, I don't really need to distribute. I can just leave it like that, okay? And now what is that? What is that, guys? That's the area of one of those slices, right? Does that make sense? That's the area of one of the slices? And so, according to what we learned earlier, you're just integrating that from an x to an x. And so, if you think about it, imagine a bunch of those semicircles stacked next to each other. Aren't they going to start here at x equals 0? And aren't they going to end here at x equals 2? Aren't they? If you stack them side by side, perpendicular to the x-axis, isn't that where they're going to start and stop? Start at 0 and stop at 2, right? Okay? All right, so that's it. So you do the same thing every time. So for these problems where you know the shape of the cross-section, it's real simple. You're simply going to integrate the area formula for that cross-section. That's it. Okay, and that's going to give you the volume of whatever that solid would look like. Okay, so, by the way, you can pull a half pi out. You might as well. I mean, you could distribute it, but that would just create more fractions in here, which would make it a little bit harder. I mean, you could do it any way you want. I don't care, but I think it's easier to pull a half pi out. And then from there, you could integrate. And then plug in the 2 and subtract what you get when you plug in the 0. Don't forget to multiply by a half pi when you're done. And whatever you get, that will be your volume. Okay? Okay, so, example 2. Any questions? Again, you guys are pretty quiet. Any questions? Yes.
What's the application of this?
If you're designing, again, if you're designing a part, if, you know, that that has a constant shape base, and then you wanted to create some unusual type third dimension that have the same slices. I'm trying to think of something that that would be designed this way. I mean, I'm sure you can imagine some things in the world that have a flat bottom and then whose third dimensional shape has the same cross section over and over, right? I mean, there are parts that are designed like that. So this is the way we would do it and be able to find the volume of any such shape using calculus. Okay? All right. Okay. So the base of a solid in example 2 is going to be a circle. Okay, now be careful. How do I graph a circle, guys? What is that? Isn't this r squared? And so r is what? R is what? 3. All right, so again, this is the bottom. This is the base. Okay? So the base is a circle, x squared plus y squared equals 9. So basically draw a circle with a radius of 3. Okay, so that's what the bottom of your solid is going to look like this time, right? Okay, so that's the bottom. And then you're going to come straight up off the paper into a third dimension using heights or cross sections that are formed with a bunch of what? Squares that are perpendicular to the what? X-axis. So what's going to happen is, if you're over here and you draw a segment through the region perpendicular to the x-axis, and then imagine coming straight up off the page, and again, I know I drew it sideways, but that actually comes straight up off the page in the shape of a square. If you're over here, it's going to be a real low ceiling, right? If you're over here, it's going to have a really high ceiling, isn't it? Are you following me, guys? Yes? So again, even though I'm drawing them sideways, these squares, they're actually coming straight up off the page into a third dimension. Make sense? Yes? Okay, so what's the area of one of those squares? Well, to find the area of a square, it's just what? The side length squared, isn't it? Yes? Okay, so now we need an expression for the side length s. Well, doesn't the side length go from the top to the bottom? Again, top to the bottom. Are you following me? All right, now this is not on your paper, so watch. Everybody watch. This is not on your paper. Let me write down that area formula for a circle. If I asked you to graph that on your calculator, how would you do it? How would you do it if I said graph that on your calculator? What would you do? Solve for y. And if you solve for y, wouldn't you get this? Wouldn't you? And by the way, and then to graph it, wouldn't you put maybe the positive 1 in y1, and then wouldn't you put the negative 1 in y2? Wouldn't you? And then when you graph these two things, that will give you the whole circle, won't it? And so you need to see something here. Are you ready? No, it's not what I want. Okay. Okay, watch this. I know which one's going to be darker? Y2, right? The negative square root one? You got it? Okay, so watch. Here it goes. I'm going to use zoom z square. Nah, that's not good. Sorry. Let's start out with the decimal window. There we go. Okay, you see the whole circle? Okay, the bottom half of the circle came from what? The negative square root? Yes? Okay. And so what we need now is we need the general distance from here straight below down to the other function. So basically you should think of this as two functions, even though it came from one equation. So this is the top function, this is the bottom function, right? All right, now let me ask you something else here. Let's go back to middle school. What's the distance from here to here? Straight down. What is it? 6. Now, how can you get that mathematically without counting? Subtract what minus what? 3 minus negative 3, which turns into 3 plus 3. And that's how you correctly get the distance, isn't it? Yes? And so, in general then, how would I get the distance from the top of that circle here, from any point here to any point below it? How would you do it? You would take what? You would take the top function minus the bottom function values, right? And so what I'm saying then is, back to my paper, to get the side length of one of those squares from here down to here, or from here down to here, you would take the positive square root, right, of 9 minus x squared, and you would subtract the negative square root, which turns into what? What does that turn into? Well, that turns into a plus, which equals what? 2 times what? Square root of 9 minus x squared. Everybody agree that that's the correct mathematical expression for the one of those sides of one of those squares? Does that make sense? Yes? Okay. And so now, what do you do with that? Well, what you do with it, that's the side length. And then what's the area of a square? Don't you take the side length and square it? So wouldn't you take that and square it, guys? Wouldn't you? And that'll give you the area of one of those cross sections or slices, right? And so what happens when you square that? When you square the 2, you get a 4. When you square the square root, doesn't it go away? Doesn't the square root go away when you square the square root? And so you get that, which, by the way, is this. Okay, what is that again? What is that again? That's the area of one slice, right? One of those square slices or cross sections. And then, finally, to find the volume of that solid, whatever it looks like, you would simply integrate that area formula from an x to an x. And so look at your picture. If you stacked a bunch of those squares next to each other, side by side, wouldn't they start here at an x value of negative 3? And wouldn't they stop here at an x value of positive 3? Wouldn't they? Yes? Okay, so now you just have to integrate that. And on some of these, I'm going to let you use a calculator, so I'll just do it that way. But you got to set it up first. That's the hard part. All right, so what do you think, guys? What's going to be the volume? 144 what? Units what? Cubed. This is a volume, right? Okay, any questions on what I did? I mean, it's the same every time. All you do is integrate the cross-sectional shape or the slice shape from either an x to an x or a y to a y, depending on whether the cross-sections are perpendicular to the x-axis or perpendicular to the y-axis. Simple, isn't it? Okay, all right, let's do a couple more and we'll be done. Okay, it says the base, you know what, why don't you guys start this one? Maybe not yet, not yet. Let's do one more together. Okay, this time what forms the base, guys? What forms the base? You tell me, what is it? All of that, right? Don't those 4 things form the bottom or base of my solid? Okay, so let's graph all that. This is a what? Y equals 4x squared is a what? Parabola, give me some points. 0, 0, what else? 1. And by symmetry, don't you have another point over here? Okay. Okay, so it's going to look something like that. This is the line y equals x minus 1, which is a what? A line going through what point? 0, comma, negative 1. What else? 1, comma, 0. Okay. What else? What else, guys? X equals 0, which is here, and x equals what? 1, which is here.
Mr. Shepard,
Yep.
shouldn't the first graph of x is 1 minus 4?
Yeah. Whoops. I should have used pencil. That's all right. I'll do it here. Why is it every time I move that thing hums? There we go. Problem fixed. Okay, here we go. Shh, guys, please. All right, so ready? Okay, so I'm going to use pencil this time. Okay, so the parabola, you got 0, 0, you got 1, 4, and so on, right? Okay, so here's the parabola. And then you've got the line which goes through 0, negative 1, and 1, 1, right? Or 1, 0, I should say. Okay, and then you have the line x equals 0, which is here, and x equals 1, which is here. Okay, so what's going on here is you got this region right here is the bottom, right? That's the bottom of my solid. And then you're going to come straight up off the page into a third dimension using what? Cross sections or slices that are what? That are what? Yep. Rectangles with a height of always 2 and perpendicular to the what? X-axis. So, if you go top to bottom here and then come straight up off the page using a rectangle with a height of 2, it'll look like that. Again, I know it's not really too high, but okay, the bottom line is you know how in some of these, like here, the closer you go to the center of the circle, the higher the roof is going to be on the solid? In this case, the roof will be constant because the height is always what? 2. Got it? You understand? Okay. But anyway. All right, so what is the area of a rectangle? What is it? Base times height, right? Or length times width. And what did we say? The heights will always be what? The heights will always be 2. All right, now what will change is the what? The length of the what? Base, depending on whether you're here or wherever, right? So the base will change. So the base is going to be a function. All right, so what's the length of the base of one of those rectangles? Well, doesn't the base go from the top function down to the bottom function? Doesn't it? And so how do you get the length of the base? You're going to take the what? The top function, which is what? 4x squared, and you're going to subtract the bottom function values, which are what? Yeah, x minus 1. So don't forget to distribute the minus there. And so do you agree you get that right there? But agree you get that? For the base of one of those rectangles, guys? Yes? Any questions? Take a look at everything I just wrote here. Any questions? See where everything comes from, guys, or no? Yeah? All right, now distribute the 2 just to make things easier. Okay, so that's the area of one of those slices, which is the shape of a rectangle, right? With a height of 2. Okay? And so over here now, to find the volume of the solid that's formed when you come off the page into that third dimension, as I described earlier, you're simply going to integrate that formula for one of the slices from an x to an x. And so looking at the drawing, where are they going to start? They're going to start here at an x value of what? 0, and they're going to stop over here at an x value of what? 1. So again, you can just punch that into your calculator, if I let you, and that'll give you the volume of that solid. Okay, guys? Good? All right, 2 more and we're done. Again, you guys are very quiet. I don't know how to take that. Is this okay or is this not okay? If it's not okay, you got to be saying something. Are we okay or not? Yes? Okay, good. All right, so this time I gave you, and they might do this on the AP test, they might give you the base without giving you any equations, in which case you might need to at some point come up with the equations. Got it? All right, so there it is. All right, now, at some point, we're going to need the equation of that line, aren't we? Because that's my top function. Yes? What's the equation of that line? Well, just, yeah. What's b? What's the y-intercept? 2. What's the slope? Pick any 2 points and count the rise and run. Or you can pick this point and this point. What's the slope? Let's say you go what? Down 2, right 4. So what's the slope? -1/2. So what's the equation? Y equals -1/2 x plus 2. Everybody agree that's the equation of that line? Yes? Okay? All right, so part A says the cross sections are what? Squares that are what? Perpendicular to the what? X-axis. Okay, so here we go. So again, if you're over here, for example, the ceiling or roof would only be that high, wouldn't it? Yes? If you're over here, for example, the roof will be as high as it is wide. Yes? Okay, and so on. So as you go right to left, the roof is going to get higher and higher, isn't it? On the solid, right? Okay. All right, so you guys, so what's the cross-sectional shape again? Square. What's the area formula for a square? Side length squared, isn't it? Which in this case is what? What's the distance between here and here? Or here and here? What is it? Yeah, it's just the function values for your line, right? And then you're going to square them. Everybody got that? And so if you want, you can FOIL. If you FOIL, you get what? 1/4 x squared minus 2x plus 4. Isn't that what you get? If you FOIL? Okay, so you're going to be integrating that formula starting at an x value here of what? 0, and stopping over here at an x value of what? 4. All right, I'm going to challenge you. I'm going to let you guys work on B on your own, and be careful. I changed some things up on you. What did I change up here on B? Yeah. This time you got cross sections that are perpendicular to the y-axis. So I'm going to let you guys play around with that and see if you can figure it out. Draw at least one of those squares so you can get a visual of what you need to set up. Okay. This is the same thing, just cross section. Okay, you guys can keep working. I'm going to get started. Now again, remember, this is the bottom, okay? So if you look at the bottom of the shape, it's going to, or the object, it's going to look like that, okay? And then, to see how high it's going to go, you imagine drawing a bunch of squares that are perpendicular to the y-axis. So, see how I drew a line segment from here to here? That's perpendicular to the y-axis. And then imagine coming straight off the paper like that. Same thing here. Go straight across. And then imagine coming straight off your paper like that. Okay, you see what it's going to look like, guys? So as you're towards the front, it's going to have a really high roof. And then as you go from the front to the back, the roof is going to get lower and lower. It's going to start dropping, isn't it? Do you understand? Okay, so obviously then, one of those slices is a square, which you're going to use the formula side length squared, right? And what is the length of one of the sides of one of those squares? Well, what's the general distance from here to here, or from here to here? What is it? Isn't it just your line function solved for x in terms of y? Okay, so you're going to have to do that. Okay, so quickly, if I want to solve that for x, I subtract 2, be careful, and then I multiply by negative 2, right? And doesn't it give me that? Yes or no? Don't you get negative 2y plus 4? Yes? Okay. And then you need to FOIL that, right? So if you FOIL it, you get 4y squared minus 16y plus 16. Is that right, guys? Yes? Is that good or no? Okay, so what you're going to do is you're going to come over here then and you're going to integrate that formula. Notice how it's in terms of y. And then you got to go dy from a y to a y. So if you're starting to stack these next to each other from the front to the back, they're going to start here at a y value of what? 0. And they're stop back here at a y value of what? 2. See how I'm going from a y to a y? Is that what you guys got or not? Yes? Okay. All right, so there'll probably be 2 or 3 of these on the test on Friday. Okay? Remember, the test is short because they do take you a while. The test is less than 15 questions. So I'd say 2 or 3 of these is a fair amount. Yes? Yes?
Is there a calculator portion?
Yes. Okay, guys? All right, so here's the deal. Let me explain. You have no book work tonight. I didn't like the book problem, so I made up my own. Okay, so for what you learned today, your assignment is this and this. Okay? It's all on a worksheet. And then this and this. So you got 4 problems, but they all have an A and a B and maybe even a C. So you got about 10 problems total for tonight's homework, right? And then I gave you the answers right here. These are the answers to those worksheet homework problems based on what you learned today. And then after that, in the same packet, what do you see? The review. Now notice, I made the review what? Optional. Only do the ones you feel you need more practice on the 3 sections. Is that clear? Okay, so look through it and do whatever you feel you need to do to prepare for Friday's test. I'm not going to make you do all of them, but there's some really good questions there. So if you have the time, you might want to do them all just for extra practice. And the bottom line is, in the time you have now, you could probably get those regular homework problems done. So all you got to do at home is maybe do some of those review problems. Okay, fair enough? Okay, but I want to collect homework right now. Okay, so I'd like what you've done so far in Chapter 6. So 6.1 and 6.2, day 1. Please put your name on them, staple them together, and turn them in.